Okay, let's start our view again. So the next topic we want to talk about is statistical inference. So literally it means we want to infer something using statistical methods or based on the sample data. And again, always keep in mind that when we're making the final conclusion, the conclusion will be upon the population. Okay? Will be upon population. And to be specific, the statistical inference we're going to discuss in this class is just the hypothesis testing. Meaning we'll be performing some comparison. We'll compare, we'll try to compare a population feature with against the reference value or compare maybe the feature, certain feature between two populations, two designs, two alternatives, and so on. So let's start with the simplest one. Let's assume I'm trying to compare a certain value or certain feature of the population against the reference value. And one example is can start with is I want to compare the population mean because the mean is sometimes can be viewed as a very representative feature of the population. So let's try to say we want to compare the population mean against a certain reference value. Now, whenever you have a hypothesis test, you always have a null hypothesis denoted as H0, and you have an alternate hypothesis denoted as H1. Now, if our focus population mean, so that means we want to do this mu. We want to compare with a certain reference value. And there are different ways you can define a hypothesis, but for null hypothesis, okay, it's always going to be equal to mu is the population mean is equal to the reference value. So the reference value can be anything. For instance, I'll use the ones in the text, but let's say mu is equal to 1.5. Now the alternate hypothesis, depending on the nature of the study, can be, well, I want to test if it's equal to 1.5 or not equal to. So the focus is to determine whether or not it's equal, and maybe equal to something is a big deal. And so in some scenarios, maybe you not so care about whether they are not equal to. You only care about if it's above this value or it's if it's below a certain value. Okay. So depending on your application, it could be any of the three. Any of the three. Okay, so this will be the null hypothesis and the alternative hypothesis, H1. Okay. And the way to carry out null hypothesis is the following. We'll discuss how it's defined. Since the null hypothesis is more or less consistent and it gives you a certainty because there's nothing else you need to worry about. So what we're always going to do is always we're going to assume this is sort of behind the curtain under the hood. We're going to assume H0 is true. Okay? We're going to make some assumption and eventually we'll see if there's going to be any contradiction display in the data. So we're going to assume H0 is true. If H0 is true, then what? Then we can usually in most cases find the sampling distribution or the probability distribution. Remember we called it whatever we have is statistic, its probability distribution is also called the sampling distribution. So if our focus is mu, then the probability distribution of x bar, the sample mean, is fixed. Okay, it's going to be fixed. And now we'll give example on how to actually find it. Now, so this is number one. Number two, calculate the actual x bar based on sample data. So in step one, what we did is, well, if we assume H0 is true, then we can figure out, well, what is the distribution of x bar? So we know the distribution. The second step, we're going to calculate the actual x bar based on the data. And since x bar is a random variable, well, it can be anywhere on the range of the distribution we figure out in step one. But in statistics, we're going to have to believe that if your assumption is true, then you shouldn't observe extreme cases. Okay? And if you observe some extreme cases, then the conclusion is going to be your original assumption is wrong. Okay. So step three, we'll look for any extremities in the x bar calculated above. If the value is extreme. We'll quantify what does it mean by extreme later. Then in statistic, we are going to make a strong conclusion that the assumption in one is actually false. And this means what? This means H0 is false and H1 is true. Okay. So pay attention to the wording I use. So I say if there's something extreme in the data based on your distribution, if it follows that distribution, well, you shouldn't observe very extreme cases. But if you observe extreme cases, then we're sort of very strongly confident that something must be wrong. And this something refers to the assumption we made in one. And that assumption is H0 is true. So if that assumption is wrong, then it means H1, H0 is false, and the alternative hypothesis is correct. So this is the idea. Well, on the other hand, if no extremes value, in other words, the value of x bar seems, or not, let's not use seems, is common. It's not very extreme, sort of a normal value that you can see. Then there's really nothing we can talk about. And the conclusion we're going to make is not going to be this strong because, well, you're supposed to be like this, right? It doesn't mean, anything. It just only mean, well, maybe we can't do much. Maybe the data is not that sufficient. Then the conclusion will be, well, then the conclusion will be weak. It's not going to be strong because you're not looking at their extreme values. So the conclusion is going to be weak. That this is the word we usually use. We fail to reject H0. Okay. This is the wording we usually say. If the value is within a certain range, it doesn't seem to be very extreme, then we say, well, maybe it's right. It's a weak conclusion. Maybe it's right. We just fail to reject H0. Reject of H0 is a strong conclusion we're making here, but failure to rejection is relatively weak. Maybe it's right, maybe it's wrong, which is not very confident which way it should be based on the data. So this is the idea. And when we want to carry out a hypothesis testing, as far as calculation is concerned, the most important step is to determine what is extreme. Because the calculation of x bar, for instance, in this case, is easier if you are focused the population mean, you use sample mean, as we discussed. It's very natural. But the thing is, how do we quantify this extreme? Okay. In all the calculations in hypothesis testing, is try to quantify this extreme. And we'll discuss how to make this procedure more specific for each of the cases we're going to discuss. Okay. So the first case is the following. The first case is the inference on the mean of a population. And let's assume the population variance is null. Let's assume this. So if this is the case, now the hypothesis testing, we always want H0 and H1. So H0 always equal to population, will be population equal to a certain constant depending on the scenario. And H1, depending on what you're interested in, could be 3 different scenarios. And we'll look at one scenario first, and then we'll extend the discussion to other cases. So it could be not equal to this, larger than that, and smaller than a certain constant. Okay. Now the assumption behind everything is what? The assumption behind everything is we're going to assume H0 is true. And if H0 is true, our sample mean should follow a certain distribution. And according to the central limit theorem, it should be equal to or approximately equal to a normal distribution with mean mu 0 and variance sigma square over n. So mu is the one you specified in the null hypothesis. We're assuming it's true, so it's here. And we're assuming variance known, so we have variance explicitly here. And is your sample size. How many samples do you have? And then if this is true, this is a normal distribution, well then we can standardize it. So number two, we'll look at a test statistic. This is the hypothesis test. We're trying to look at the extremes in ENGR in this particular case, if it's related to mu. So we're going to introduce a test statistic. And the test statistic is very simple. It's just we're going to standardize this normal random variable. So assuming it's true, so we'll be taking x bar minus mu 0 divided by a standard deviation, so it'll be sigma over square root of n. Now mu 0 comes from our hypothesis. Sigma is assumed to be known, n is the number of samples, and x bar, the value of the sample mean, can be calculated as soon as you have obtained the data. So, how do we define those extremes? Now, extremes are usually defined by what we call critical values or critical region or rejection region. And this is what we know. If H0 is true, then Z0 should be a standard normal random variable, as we all know it. And if that's the case, these two tails appear to be some extreme values, some extremes. And if we can quantify this range, then we're able to determine, well, if your actual test that's calculated is going to be extreme or not. And the extreme is quantified as the follows. So we're going to look at the probability contained in this specific tail, and we want it to be alpha over 2. In this part also we want it to be alpha over 2, where alpha is a small number, usually 5%, 1%, and so on. Okay. It is usually referred to as the level of significance or significance level. Level. Okay. You can take values, for instance, 5%, 1%, depending on the application. And that's the case, since the tail will be alpha over 2, then we'll define this specific boundary or this value that gives you this tail to be z sub alpha over 2, and here also z alpha over 2. So for instance, if alpha is equal to 0.05, meaning 5%, then we'll be looking at z 0.025. Okay, so here will be negative sign. And by looking at the table, you can easily find what this number is going to be. Okay? You just need to find the probability that is equal to 0.025. Or in the table, our book, we just need to find the value that will gives you the opposite of that. The opposite of that. So it will be equal. This means what? This means the probability that a standard normal distribution less than the specific value is equal to 99, sorry, 97.5%. So if alpha is equal to 5%, so this will be 2.5%, 5.5%. So if we're standing on this value and look all the way to the left, that will be, of course, 1 minus 2.5%. So that will be 97.5.